Okay, so when it comes to farming, water is pretty much everything, right? But getting that perfect amount to the crops, that's a massive challenge. For decades, we've been leaning on this one specific formula to get it right. But what if that formula has a tiny but crucial flaw? And what if the solution is AI? Let's dive in and see how we can use some pretty smart tech to tackle a global thirst problem.
So here's what we're going to do. First, we'll get a handle on the sheer scale of the global water challenge for farming. Then, we're going to expose a hidden weakness in a classic formula. After that, we'll see how AI swoops in to save the day, and we'll even have a little accuracy showdown between different models. And finally, we'll wrap it all up by looking at what this actually means for the future of farming and saving water.
All right, let's kick things off with the big picture, this global thirst problem. Look, managing water for our farms. It's honestly one of the most critical challenges we're facing as a planet. And it's not just about having enough water, it's about being really, really smart about how we use every single drop.
So think about it. How do you actually figure out how much water a huge field of corn needs? I mean, you can't exactly walk up to a stalk and ask if it's thirsty, right? And that's the fundamental challenge for efficient farming. How do you measure what crops need, accurately and on a massive scale?
To get around this, scientists came up with a really clever idea called reference evapotranspiration, or ETO for short. The best way to think about it is like a universal thirst score for a perfect, standardized green field. If we can nail down that number, we can make way smarter decisions about watering crops. And this doesn't just affect one farmer's sprinkler system, it impacts a whole country's water strategy.
Okay, so now let's talk about one of the classic tools that's been used for ages to figure out this ETO number. It's super useful, especially in certain situations, but it's got this one little nagging problem, a flaw that turns out to be pretty significant.
The method we're talking about is called the Blaney-Criddle method, and its biggest selling point, it's simple. You can get a decent estimate of how much water your crops need using just temperature data. That is a huge deal in places that don't have all the fancy, high-tech weather stations.
But, and this is a big but, here's the catch. To make the Blaney-Criddle formula work, you need this one special value called the B factor. And the old school way of finding this B factor is, well, it's just clunky. You literally have to look up numbers in a big table and then do a whole bunch of calculations by hand. And as the paper we're digging into points out, this whole process can lead to considerable error. You know, a chain is only as strong as its weakest link, and this was a really weak link.
So you might be thinking, why not just use a more modern formula? And you're right, there are others, like the Penman-Monteith method, which is kind of the gold standard. The problem is, it needs a ton more data. Things like humidity, how much sun there is, wind speed, the whole shebang. That kind of detailed info just isn't available everywhere, and that is precisely why fixing the simpler Blaney-Criddle method is so important. It could bring more accurate water management to the very places that need it the most.
Okay, and this is where things get really cool. Instead of messing around with those old lookup tables and manual math, what if we could just use AI to predict that tricky B factor with pinpoint accuracy? This is where this awesome field of AI, called soft computing, comes onto the scene.
So what exactly is soft computing? Well, think of it like training a computer to be a super smart detective. You don't give it a rulebook, instead you just show it a ton of examples. The clues, right? In this case, you show it the weather data and the correct B factor that goes with it. The computer then just figures out the hidden patterns all by itself. It's kind of like creating a digital expert with perfect intuition for problems that are too messy for simple rules.
So, to figure out the best way to predict this B factor, the researchers basically set up a competition, a bake-off, if you will. They took 5 different soft computing models, each with its own special way of learning, and gave them all the same data to chew on. The goal was simple. Which one of these AI contenders could replace that clunky old table with a super accurate prediction?
Okay, so it's time for the accuracy showdown. Let's see how our AI models actually did and find out if this whole high-tech approach was worth it.
And wow, the results are in, and they are pretty incredible. Just look at this table. One of the models, the one called SVR-rbf, it just completely blows the others out of the water. It got an R-squared score, which is just a fancy way of saying how well its predictions match the real data, of 1.000. I mean, that's a perfect score. And its average error, less than 0.5%. That is a massive leap in accuracy. And this is such a cool way to see the results. It's called a Taylor diagram, and you can just think of it like a dartboard. That black diamond that says actual, that's the bullseye. That's perfection. Each of those colored dots is one of our AI models. And you can see, yeah, most of them are pretty close. But look at that light blue dot for the SVR-rbf model. It is right on target. It's just a perfect visual of how incredibly accurate this thing is.
So what does that 1000.00 score really mean? It means the model's predictions were in perfect lockstep with the actual values. It's like the AI cracked the code. It figured out the secret recipe for predicting the B factor, with basically zero error. At least for this one little part of the formula. The whole problem of guesswork is gone.
Okay, so a super accurate formula is great for scientists, but so what? What does this actually mean for farmers, for you and me, for the planet? Let's get into how this precision can help us save a whole lot of water in the real world.
So to really put this new AI-powered formula through its paces, the researchers ran a real-world test. They took a whole year's worth of actual climate data from a city called Nice in the former Yugoslavia. Then, they calculated the total amount of water that would be needed for the entire year. This was the moment of truth, to see how much of a difference all this accuracy makes when the rubber meets the road.
And check this out. The results are pretty striking. One of the older, common methods for estimating water use was off by over 5%. Now that might not sound like a ton, but think about it. Over an entire year for thousands of acres, that means you could be seriously underwatering your crops. But the new AI model, it was only off by 0.5%. That's an incredible improvement in getting the water use just right.
So here's the bottom line. By using a little bit of AI to fix one tiny flawed piece of an old but still really useful formula, we can make our big picture water calculations way more accurate. And more accuracy means smarter irrigation. Smarter irrigation means better crops. And most importantly, it means we waste a whole lot less water.
You know, this whole thing just shows how powerful AI can be when you aim it at a very specific problem. And it leaves us with a really big question to chew on. If a bit of machine learning can help us manage something as vital and fundamental as water more wisely, what's next? What other huge resource challenges could we solve with this kind of thinking?